Hello everybody, and today we'll be going over tutorial 6, which is majority, actually all of it is on the Routh-Hurwitz criterion for stability. So let's jump in. So exercise number 1 is we're going to use a criterion in order to actually figure out the stability of this problem. So we'll jump in on the next page. Starting out with this question, we're going to go by labeling our s's on the left hand side here. So we have an s to the 4, that is our highest power. So s2 all the way to s0. We're going to have our squares up front. So we have a 1, 10, and then 80. And we have a 5, we have a 10, and a 0. And for simplicity's sake, I'm just going to label these. And then we'll evaluate as we go through. Alright, so following the criterion that they showed you in class, we know that A is equal to 1 over negative 5, because 5 is in this placeholder, negative 5, and we're going to take the determinant of here, so 1, 10, 5, and 10. That's going to equal to 10 minus 50, all over our negative 5, which then evaluates out to 8. So A is equal to 8, so pretty simple. Same with, we'll go with B, which again will be 1 over negative 5, 1, 80, 5, and 0. 0 minus 400, all over negative 5. So what we'll have here is we'll have a positive 80. Next we'll go to C, which will be 1 over negative A, and we found out that A is negative 8, so 1 over negative 8. Then we're going to do 5B. We figured out B was 80, and A was 8, and this is 10. So now we're looking at, this section right here. So we're going to have 400 minus 80 all over negative 8 is equal to negative 40. So we'll have a sign change there. So now again we'll go, we'll calculate D, and for the sake of this, add another 0 here because we know there's not going to be a value there. We'll have 5 times 0 minus A times 0, which I'll evaluate it to 0 no matter what. So we know D equals to 0. We have E. And E is going to equal A times D minus C times B times 1 minus negative C. So C was negative 40, so times that by minus 1, and we get a simple 40 at the bottom. And we'll have a look. A times D, we figured out that A was 8, and D is 0. And C and B, C was negative 40, and B was 80. And so that equals to 0 plus 3,200 all over 40, which is equal to 80. So now what we'll do is we'll write out our final values. So we have s to the 4, s to the 3, 2, 10, 1, 10, 80, 5, Okay, so now we have completed our table, and what we notice is in the first column we have two sign changes. And therefore we know that the system will be unstable. And that is the solution to question number 1 of your tutorial. Okay, now looking at exercise 2. So what we're studying here is the stability of the motorcycle with the rider on top of it. And we want to know what ranges of the variable k can we have and still remain stable. So we have two parts to this question. Part A is where we're actually going to ignore the zeros in the numerator and as well as the insignificant poles in the denominator. And then B, we're actually just going to calculate the full range of k. And it's a much longer solution, but you actually get a wider range at the end. So we'll go over that step by step. So moving on to part A, first of all, it states that we can ignore our zeros or cross them out. And then it also states that we can eliminate insignificant poles. So if you remember from lecture 9, we actually went over how to do this. And so I'm going to just walk you through it again real quick. So we know our poles are going to be at 0 from the first one, -20. And then we have two systems here, so we'll calculate this at the bottom. So what we get is we get -5 plus or minus 10j. And now we'll have a look at this second part down here. And so we have -60. Alright, so now we have found all of our poles. So I'm just going to list them all here at the bottom. So we have a pole at 0, -20, -5, plus or minus 10j, and -30, plus or minus 50j. As you remember from lecture 9, insignificant poles are poles that are 5 to 10 times greater than the smallest real value of the other poles. And that doesn't include 0, because 0 times 5 or 10 again is 0, so we don't include that. So our -5 plus or minus 10j would be the smallest pole with a real value. So our magnitude is equal to, we're going to do 5 times for the sake of this example, so it actually gets rid of a set of poles. So 5 times minus 5 is -25. So that means any pole with a real value u less than 25 is considered insignificant. So we can actually cross it out. So since we know this, we can actually cross out this last system here, so we don't have to include it in our stability criterion. And as you see later on when we do the full solution, this actually helps a lot because the full solution becomes very long. So what we'll do now is we're actually going to draw out the transfer function. So if you look at the question, it actually states k for a unit negative feedback. ls is just our transfer function, so we actually have to create a control system out of it. So this is what we're going to do. We'll draw it up top. We have rs into a summing block to our function ls. this goes out to ys. And again, the problem stated that it's a negative feedback loop, so we can continue on. So I'm going to simplify this real quick. So y of s So now if we expand and simplify the bottom, we get the following. We have k all over s to the 4 plus 30s cubed plus 325 s squared plus 2500s plus k. So now we're going to move on to the next page and actually complete the stability criterion for this, and we'll only be using the denominator. So the denominator was equal to s to the 4. So we have this simplified denominator after we crossed out the insignificant poles as well as the zeros. So we're going to put this in our stability criterion. So now we're going to start out by just finding our value of a. So a is equal to 1 over negative 30 Okay, so we'll evaluate this as 2500 minus 30 times 325 all over negative 30. That comes out to positive 241.67. Now if we continue with b, we have 1 over negative 30 again. That doesn't change. We have 1k, 30 and 0 equals to 0 minus 30k all over negative 30. So our value for b is k. Okay, so c, we're going to have 1 over negative a and we're going to have 30 times b, 30, 2500, a, and b. B's small, so I'm going to write it in here. It's equal to 30k minus 2500a all over negative a. So if we evaluate this, subbing in for the value of a, we get the following. We have c is equal to 30k minus 604,175 all over 241.67. Again, if there was a value in here, we know this is going to be 0 because 30 times 0 and a times 0 is 0. So d is going to be 1 over negative c, a, and then b, which is just k. And we have our value of c again and 0. So that equals to A minus ck all over negative c. So again, d is just equal to k. So now we're going to write this out nicely on the following side. So there actually is, we forgot a negative sign with the value of c, so I'm just going to add that in there. So that's important, and we'll get to why that's actually important a bit further on. So we have 30k minus 604,175 all over negative 241.67. And then our final value of S0 or D is K. Alright, so in order to keep all the values in the first column positive, we know, first of all, K has to be greater than 0, and 30K minus 604,175 all over 241.67 has to be greater than 0. So what we can do is we can multiply this negative in the denominator into the numerator, and we can multiply the denominator by the 0 to get rid of it. So we will have negative 30k plus 604,175 is greater than 0. So we can bring the k to the right hand side to make it positive. So we have 604,175 has to be greater than 30k. Therefore, k has to be less than 20,139, roughly. There's a couple decimal points on there, but we can ignore those. So therefore, the system is stable when the value of k is greater than 0 and less than 20,139. And that is a range of k for part A. We will now continue on to part B. So now we're going to go to section B. With section B, it didn't want us to eliminate any zeros as well as any insignificant poles, so we're actually going to leave the whole system together and evaluate the whole transfer function. And you'll see the benefit of actually removing zeros and removing the insignificant poles, because doing the stability criterion, it's actually going to take a lot of time, and so we'll see this as you go through. So we're going to start out, we know we have our transfer function. Okay, and so we're going to do a closed loop transfer function of this big system up here. So as you can see, since we didn't eliminate any zeros or any insignificant poles, your denominator actually becomes quite big. And what happens is you can simplify it to the following function. So as you can see, it's quite a large transfer function, and it takes up most of our initial screen. So what we're going to do is we're going to go on to the next page, and we'll actually do the stability criterion for this system. Alright, so we're going to go ahead and write out all our values of s that we know. Alright, so now looking at this, we're going to start with evaluating number, or a. So a is going to equal to 1 over negative 90. It's equal to 124 minus 90 times 5525. result is 5,387.22. Again, we can do the same thing with b, 1 over negative 90. Evaluate this out, we get 85 times 10 to the power of 5 plus 30k minus 90 times this, so I'm going to pull out the 90k in front, also minus 11295 times 10 to the 4. So as you can see, these numbers are getting quite large, all over negative 90. So if you simplify that, you'll get the following. Since we have some higher negative numbers, we're actually going to take the negative from the bottom and bring it up to the top and make it positive. So doing that, we get 60k plus 10,445 times 10 to the 4 all over 90. So that's our value of b. So again, similar method, we're going to go to c. c is 1 over negative 90. We have 1, 5k, 90, and 0. So our result for c will be 0 minus 90, 1125k, all over negative 90. So c is equal to 1,125k. So that one's pretty straightforward. So knowing that, we can go ahead and we can calculate d. So d is equal to 1 over a. And for now, I'm just going to, or 1 over minus a. And for now, what I'm going to do is I'm just going to sub in the letters, and then I'll evaluate them and just give you the answers. What's going to happen now is we're going to have a lot of math to complete, and for the sake of your time, I'm just going to spit out the answers so you can try it by yourself. Right, so that's the evaluation of D. Continuing on to E, we have, again, 1 over negative A, 90 over A, 35 times 10 to the 5 plus 30k all over C. So again, we have 90C minus A that evaluates to an even greater number. Okay, and so as you can see, since we didn't get rid of the insignificant poles or the zeros, it's actually becoming a quite large problem with these huge numbers within them. So now we will continue and we'll have a look at F. And F again is going to be 1 over negative D determinant of A. So for the sake of time, I'm actually going to just speed it up for you. So what it shows is if you evaluate all the math correctly, that the final range of K is from 0 to K. Okay. So this would be our final range of K if you continued on with the math. And what you notice here is this range of K is actually with or greater than the range that we found for the values with the zeros and the insignificant poles taken out. So if you remember in part A, our result was between 0 and 20,139. So this final range of K for the whole transfer function encompasses part A, so you know that it's true. So, and this also shows you the benefit of neglecting zeros as well as insignificant poles. It can actually significantly shorten the process that you have to take to find the stability criterion. Okay, now moving on to problem 3. And so what this is we have a closed loop control system of a aircraft designed for vertical takeoff. So we have our actual path and our desired path, and we want to determine what range or values of K we can have while still being within a stable system. So we're going to go forward with this. So first thing we got to do is we got to find the transfer function of the system. So we'll go ahead and we'll write that out. And right away I'm just going to put it into the full form. And if we simplify that, we get K s plus 5 all over s cubed plus 18s squared plus K s plus 5K. Alright, so that's our transfer function. So now we're going to do the stability criterion on the bottom, and we'll go forward in that method. So we have s to the 3 is our highest power. So we have a 1, and then we have a k minus 40, an 18, and a 5k. Okay, so again, we're going to solve for A, B, C. All right, so A is going to equal 1 over negative 18, 1 k minus 40, 5k, relative to 5k minus 18 k minus 40 all over negative 18. Going forward, B is equal to actually 0. Now we'll go forward with C. 1 over negative A. So this whole system here. So I'm just going to write negative A. And we're going to have 18, 5k, A, and 0. So we're going to have 5k, negative 5k times A all over negative A, which equals to 5k. Okay, so in order to ensure stability, we know that A and C have to be greater than 0. Okay, so for C to be greater than 0, so for C is greater than 0, we know that K simply has to be greater than 0. Okay, so that simplifies that. Then our last term is A. Okay, so we have 5k minus 18k minus 40 all over negative 18 has to be greater than 0. So this is for A is greater than 0. Okay, so we'll bring the times the negative to the other, the 18 to the other side. The negative we have to reflect up at the top here. So we're going to have 18k minus 720 minus 5k. Again, we took the negative from the bottom and brought it to the top. Has to be greater than 0. So that equals to 13k has to be greater than 720, or k has to be greater than 720 divided by 13. Okay? So from this information, we know that the system will be stable when k is greater than 720 over 13, and the system is going to be marginally stable, which means it's on the brink or change from unstable to stable, so it's right in between. And this is going to happen right at this condition, so when k is equal to 720 divided by 13. And that is the final answer for question 3. Alright, now looking at exercise 4. So what we have here is we have another closed loop transfer system. And what we actually have is we have some disturbance, or this value TD within. So for the purpose of this question, we're actually going to do superposition. And we're going to say that this is going to be 0. We're just sort of going to eliminate that source coming into our system as we analyze it, just to make it a little easier. So what it wants us to do is plot the relationship between the controller gain, Kp, and Kd that results in a stable system. So what we're going to do is we're going to do the stability criterion, and then from there we can determine the correlation between Kp and Kd, and from there we can actually plot our final result. So moving on, again, we got to make a full closed loop transfer function. So we have y of s for r of s, to the following. and then that evaluates out to Kp, Kds, and your simplified denominator will be s cubed plus 9s squared plus Kd plus 26s plus Kp plus 24. Alright, so what we're going to do is we're going to put this into our stability criterion. Squared to 1. We have 1 Kd plus 26. We have 9 Kp plus 24. Alright, so we'll solve for A and B. So A is equal to 1 over negative 9, 1 Kd plus 26, P plus 24, and that evaluates the value of A, which will be Kp plus 24 minus 9 Kd plus 24 all over negative 9. Okay, so we can't actually evaluate that or going forward, and this factor is actually going to be 0 because we have nothing to multiply it by in that scenario. And then so when we look at our next equation to find B, B is going to be equal 1 over negative A, 9 Kp plus 24, A, and 0. So B is going to equal to negative A Kp plus 24 all over negative A. So the negative A's cancel out, and you're just left with Kp plus 24. So this gives us a good start. Again, we know A has to be greater than 0 and B has to be greater than 0 in order to have stability. So when B is greater than 0, that means Kp plus 24 has to be greater than 0, which means Kp has to be greater than negative 24. Okay, so that's our first constraint in here. Now looking at A is greater than 0, so we take what we have down here. Actually, there's a mistake in this solution right here. Instead of a 4, this should be a 6. Okay, and so we have to make this greater than 0. So we have Kp plus 24 minus 9 Kd, and then minus 9 times 26, minus 234, all over negative 9 is greater than 0. So what we're going to do is we're going to bring the 9 to the right hand side, and we're going to multiply the negative 1 in at the top, and then we're going to bring Kd to the one side. So we have 9 Kd is going to be greater than, we're going to shift everything now to the other side, and we're going to do 234 minus 24 is 210. So we have minus 210. Our Kp is coming to our other side, and since it's timed by negative 1, and bring over, it's going to be positive Kp. And then what you have is we can bring this 9 over to the bottom. Give it 9. And that gets our final result. So what we can do now is we can actually plot it on a graph. So we can see what range of a variable for Kd, like what the combination of a Kd and Kp together can achieve. Alright, so the first thing is we know Kp, it always has to be greater than negative 24. So we're going to label this negative 24. And what we can figure out now is we can figure out the intersect with the KD axis if we set Kp equals to 0 in this equation up here. Okay, so we have negative 110 divided by 9 gives us negative 23.33. So negative 23.33. So that'll actually be our intersection with the KD axis. Alright, so what we can do is we now know our slope will be Kp over 9, and so we know that for every 9 steps in the Kp direction, we're going to increase 1 step in the Kd. So I'm actually just going to roughly sketch this out. And so everything in this area here, with terms of values Kd and Kp, with the range, as long as it fits within this plot, it'll be considered stable. And that is all that tutorial 6 encompasses. Please let us know if you have any questions. If you understand this and you went through this tutorial pretty well, you have a solid grasp on Routh-Hurwitz criteria and how it works to find stable and unstable systems.